Hi everyone, in this video I want to start talking about solving exponential and log equations. So the basic tools that I want you to keep in mind as we're doing this are just like you could square both sides of an equation or square root both sides of an equation or add 5 to both sides of an equation, you can also take the log of both sides of the equation or exponentiate both sides of the equation. Meaning if you have a something equals something type statement, you could raise both sides up and put them in the exponent as long as you're using the same base on both sides. And you could also take the log of each thing and expect them to still be equal to each other as long as you're using the same base on both sides. Here we do have to be a little careful. X could equal y, but if they're 0 or negative, this is not a legal statement to make. So if we're going to introduce logs, we want x and y to be non-negative numbers. What else? If we eliminate logs from an equation, having a log in an equation introduces some domain restrictions. So getting rid of them, we lose track of some of those domain restrictions, and we might possibly introduce an extraneous solution. So anytime we're solving an equation that starts off with logs in it, we always want to check for extraneous solutions. Even if we are 100% sure we did not make a mistake, we could have a bad solution. Okay, so I'm just going to start working my way through some that aren't very messy and see if we can figure out the tricks that we need. But again, basically that's it. If you need to eliminate logs from an equation, you should exponentiate. If you need to eliminate exponential pieces of an equation, you should take the log of both sides. Do be really clear that the entire left and right hand sides have to go up into the exponent with a single base b if you exponentiate. And same thing with logs, the entire left and right hand side have to go inside the two logs. You can't split that up into several logs. So be really strict with yourself on actually doing the step where you exponentiate or take the log. Okay, first pair. Again, we're going to start off with things that hopefully aren't too messy and see if we can be really careful and figure out all the tricks along the way. So here, if I'm trying to solve for x, I'm hoping to get rid of this log because there's no base. I'm assuming that's a common log, log base 10. To get rid of a log base 10, I would need to use an exponential with a base of 10. So this is going to be an exponentiate step. If these two things are really equal to each other, then 10 to the log of x should really equal 10 to the negative 3. And the 10 to the log of x, that's composition of inverses, so those two should wipe each other out. If I take the log base 10 of something and then raise that to the 10, I should just get my something back. The 10 to the negative 3 is 1/1000th, and there's my answer. I do want to check. This is a not optional check. My pen's dying. Let's see if I have my green one handy still somewhere. I do. Okay, so we need to check and make sure that we don't violate any domain restrictions in the original problem. So if we plug 1/1000th in, it is completely legal to take the log. So I don't have any domain problems, so it's not extraneous. If you want to check a little bit more thoroughly, you can actually ask yourself 10 to what power gives you 1/1000th and see hopefully that it is in fact negative 3. So not only is that not an extraneous solution, it also appears to be a good solution, the correct solution. Okay, so to get rid of logs, exponentiate. In this next one, it's a little tricky because the bases actually are unknown. So if I want to exponentiate to get rid of a log base x, I will have to use a base x. X to the log base x of 81 should just give me 81. So I'm working on 81 equals x to the 4th. So interestingly, because here the variable was actually the base, this turned this into a 4th degree equation. I now want to get rid of a 4th power. We do need to be a little careful. There are two things that we can raise to the 4th to get 81. So basically we want the 4th root of 81, which is 3, but we should get a positive or negative 3 for our x. So if you're introducing an even root, you need a plus or minus on that. let's see, what else do we want to say here? We are looking at, so we do need to check here, but this is actually kind of a different check. It's not a domain thing. When we talk about the domain of a log, we're talking about what we plug in as our input. This is a base thing, so the rules are very slightly different. The input of a log has to be positive. The base of a log has to be positive and should not equal 1. We don't have 1 here, so that doesn't end up mattering very much, but we do have a negative possibility. So in the end, we're just going to say x equals 3 is our only solution. Okay, let's see. So this one is an exponential equation. The variable is stuck in the exponent as opposed to the last two where the variable was in some way stuck in the log statement. If we want to get rid of an exponential statement, I'm gonna yawn, sorry guys, we need to use logs. The truth is you can use any log you want. Log properties will allow us, even if our log base doesn't match our exponential base, to move the power down in front. My advice is to be smart about choosing your logs. If you want to cancel out an exponential with base 3, the neatest, cleanest way to do that is going to be to use a log base 3. So I get a log base 3 of 3 to the x equals log base 3 of 7. Okay, so you can take the log of both sides of an equation, and you should choose that log carefully to give yourself the least possible amount of work. Log base 3 of 3 to the x should just give me x. What power of 3 is 3 to the x? Those are inverses. And log base 3 of 7 is nothing particularly nice. If I had the log base 3 of 9, I would be asking myself what power of 3 gives me 9, and I would say it's 2. But if I'm asking myself what power of 3 gives me 7, it's certainly not any sort of nice, easy to write down power. So this is a completely acceptable answer. That's one of the things you want to get used to in this section is your answers can involve logs. You just don't want any variables on this side. So the log base 3 of 7 is just a number, and that's a completely acceptable answer to an equation. So to get rid of logs, we use exponentials. To get rid of exponentials, we use logs. On the fourth one, we're back to a log equation. So here, if I want to eliminate a log base 1/2, I will exponentiate. And as you get comfortable, I'm okay with not seeing this step. I want you to understand that that is the steps that gets rid of the logs. But if you can see what's happening here, you don't have to write out the exponentiate step for me. Okay, so this is what I end up with, and this actually works out beautifully. This equation might have looked messier at the beginning, but it's going to clean up really nicely. Both sides we have a log that can cancel out. So I'm left with just 2x plus 1 equals x plus 3. And that's just a linear equation. So I'm going to subtract x from both sides. And I will get x plus 1 equals 3. And then I'll subtract 1 from each side and get x equals 2. Oh, and I boxed that off, but this is another one. We started with a log equation, so there's a not optional check here. If I plug 2 in, I get the log for 5, which is completely legal, log base 1/2 of 5. And on the other side, I also get the log base 1/2 of 5, which is not only also legal, meaning that it's definitely not extraneous, but I got the log base 1/2 of 5 equals the log base 1/2 of 5, and I am confident that that is a true statement, so that's definitely a good solution. Okay, next. Another exponential. Again, you can actually use any base you want, but if you're being smart, I would say that a natural log is going to be a really good choice here because it will just straight up cancel out the e to the 4 minus x. So I'm going to try that. I'm going to leave a little room so I can show you if I use a different base what happens. Okay, so we're going to take the natural log of both sides. And on the left-hand side, that's going to wipe out the exponential. So the natural log of e to a power should just give me the power. 4 minus x equals the natural log of 11. And then I will subtract 4. And multiply everything by negative 1. Okay, so there's my answer. And this is a perfectly good and correct answer. I just want to sneak in over here, see if I can fit it. What would happen if I had chosen a different log? So I'm going to use common log. If I use common log, the first thing I would do is bring the power down to the front, since the log doesn't just cancel out the base. So even though I'm not getting that really nice clean cancellation that I got when I used a natural log, I did get the variable out of the exponent, which was my big goal. If you're trying to solve for x and x is stuck in the exponent, that's a problem, and logs will help you fix that problem. You could distribute here, but actually I think I'm going to go ahead and divide. The x is stuck in the parentheses. It's the one and only x, so dividing this will actually kill it all in one step. Often I make you distribute things in so you don't build fractions, but I think I'm okay with the fraction here. Log of 11 over log of e. And then steps are starting to look really familiar. Subtract 4 and multiply by -1. And you'll see what we get. Oh, hold on. Let me be careful. Multiply by -1, that becomes a +4. What we get doesn't look like the same thing we had before, but if you think carefully, it actually is. A change of base formula will confirm that it's the same thing. So if I wanted to take the natural log of 11 and change that to common logs, I would just go ahead and do it. So there's the common log of 11. And then I would divide by the new log of the old base. So common log, and the old base was e for a natural log. So those are actually the exact same thing. Okay, last one here. If we have the natural log of 11x equals the natural log of x minus 5, my x's are stuck inside of natural logs, so I'm going to exponentiate using a base of e to try and cancel out the natural logs. Natural logs have a base of e, which means exponential base e is their inverse. Again, if you're comfortable, I don't actually have to see this in-between step here. If you can see what's going to happen, it's all right to go ahead and just write it out for me. Basically, the only way that the natural log of 11x is going to equal the natural log of x minus 5 is if we can make 11x equal x minus 5. I'm going to subtract an x from both sides. So I get 10x equals -5. Divide by 10. X equals -5/10, which is -1/2. This was, let's see if I can talk and write at the same time. This was a log equation, so I do need to double check. This is one of those non-optional texts. If I plug in -1/2 back in, I get natural log of -11/2. I cannot take the log, any log, of a negative number, so this is actually not a good solution. You could check the other side if you want, and you'll run into the same problem. Basically, the only way to make 11x equal 5 minus x is if both are negative, in which case we can't plug either one into the log, so it's not possible to get the same thing out of the log. Because I had only one solution and I had to throw it away, I'm going to go ahead and say no solution. So no solution to that equation. All right, long video, I know. I've got a couple more I want to do on this one. Okay, so 3 more. Log base 2 of x squared plus 5x plus 10 equals 4. All right, so I've got my variable stuck inside of a log, so I'm going to go ahead and exponentiate with a base 2 to get rid of that. If you're comfortable, you don't have to show me this step, but make sure you're really clear on what exactly is happening here, or you're going to get in trouble. So we push the log base 2 up into the exponent, and we push the 4 up into the exponent. This is a spot to really watch out. People will flip-flop, and they'll do 4 squared instead of 2 to the 4th, which interestingly here wouldn't get you in trouble, but generally it would get you in trouble if you flip-flop those. Okay, so 2 and log base 2 are inverse operations, 2 to a power in log base 2. So we're just going to be left with the x squared plus 5x plus 10. And then 2 to the 4th is 16. This turned my log equation into a quadratic equation. So let's go ahead and subtract the 16. And that looks factorable. I think I can go x plus 6, x minus 1. which means x could be -6 or x could be 1. We have our non-optional check here. This is a log equation. Okay, so if we check the -6, we get 36 minus 30, which is 6, plus 10, which is 16. So log base 2 of 16 equals 4. Okay, so it's definitely not extraneous. I'm not getting any domain problems on my log. And even more than that, I can say that it definitely looks right. 2 to the 4th is 16, so that's a good sign. If I check the x equals 1, I get the log base 2 of 1 plus 5, 6 plus 10, same thing, which means once again, not only is it not extraneous, I don't have any domain problems here, it's also a completely true statement, so I'll get to keep both answers here. Okay, 2 more to go. This one is exponential. I would like to get the variable out of the exponent. Because this is an exponential with a base 10, I'm going to use a common log. Once again, you could actually use any log you want and it will work, but it will be a little bit less messy if you choose a log that cancels out part of this. In particular, I really like canceling out the 10. You could choose a log base 24 though, and then this would work out really nicely. Okay, so if I take the log of 10 to the x squared minus 1, I get x squared minus 1 equals log of 24. And this looks sort of terrible, but remember, we're solving for x. So in this case, I only have one x on one side of the equation. I can just reverse order of operations to solve for it. You also have the possibility of using a quadratic formula on this. You could set it equal to 0. If you're going to do that, I would just point out that you need to realize that your a is 1, your b is 0 because there is no x, your c would be -1 minus log of 24. That whole thing is your c. So feel free to check that out if you're interested. You should get the same answer. What I'm going to do is add the 1. Be really clear here that you cannot add it to the 24. The 24 is stuck inside of the log, so you'd have to take the log before you can add. And then we can square root both sides. Don't forget your plus or minus. And there are 2 possible answers. I don't have to worry about extraneous solutions here. I didn't start with any possible domain problems. This is exponential, so that's not going to happen. If you want to step through, square this, square will get rid of the plus or minus for you. You'll get the log of 24 plus 1 minus 1. The 1s will drop away, then the 10 to the log of 24 will give you 24. So it does check out, but you do not have to check that one for extraneous solutions. Okay, last example for this video. 2 times log base 3 of x equals log base 3 of 2x. This seems like it's not a big deal to solve, and actually it isn't, but there's one really easy mistake to make. I right away notice that I have a log base 3 on both sides, and I would like to exponentiate with base 3 to get rid of those, but you have to be really careful. Order of operations here is you plug in x, you take the log, you then multiply by 2. If you exponentiate, that would happen after the multiplication, not after the log. And if you want 2 things to cancel out, they have to happen one right after the other in order of operations. So we have to deal with this 2 before we can get rid of the log. It's easy to do, you just have to remember to do it. So I'm going to go ahead and make that 2 a power. Now I can exponentiate with a base 3. As soon as you get comfortable with what exactly is happening here, feel free to stop writing this step that I'm writing down right now and just say that x squared will have to equal 2x. Okay, this is a really good one. You want to be careful right here. People are very tempted to divide by an x. The problem is that if you divide both sides of this equation by an x, you lose a solution. So just like multiplying both sides of an equation by something with a variable can introduce a new solution, dividing can lose a solution. The alternative, anytime you're tempted to divide out your variable, is to move everything to one side and instead factor it out. Factoring, oops, no squared anymore. Factoring it out is dividing it out. It's just that it doesn't disappear completely. It stays sitting out in front. And you can see that you get solution x equals 0. That's the one you would have lost if you divided. And you get solution x equals 2. It was a log equation, so we better double check. And it turns out that that one we would have lost, we actually wouldn't miss very much, but you can't take for granted that that's always how it's going to work. So I do throw away the 0 because I can't take the log of 0. 2 looks great. It's completely legal to take the log of 2, so I actually only end up with the one solution. All right, thanks for watching.